So this is our 3D stereolithographic 3D printer, and we're able to build physical models of digital models that we've created. Essentially, there's UV curable resin that we trace a laser over the cross section of the part, and it turns that liquid into a solid. Then a Z stage basically increments it layer by layer, and we're able to build up a physical model. So most of the printers that you see on the market right now are extrusion. Essentially, it's like a very small hot glue gun. What we've done is been able to increase the resolution by an order of magnitude by using the fine-tuned precision of a mirror turning with fine electronics with the laser beam instead of with a hot glue gun, essentially.
So this is a self-leveling tripod. Originally, we wanted to apply it towards nature photography with uneven ground. It would level itself so you don't have to go through all the manpower. Basically, over here there's an on-off switch and up and down, so you can move it up and it'll level. You can move it down. And you can move the legs anywhere you want and it'll just level itself. There's just 3 linear actuators and accelerometer that checks the tilt values and it'll go back to 0. There's a lot of power in mechanical engineering. Maybe we need some mechanical engineering photographers and artists to come up with some cool ideas.
So this is a desktop greenhouse. It's controlled by a web app. The user inputs the temperature and the light that they want over the course of their day. Then the greenhouse controls the light with an LED array and digital light sensor, and it controls the temperature with a digital temperature sensor and a thermoelectric cooler, and it has 2 fans. So we mostly intended this to be used to grow plants indoors. We thought it might be nice for somebody who lived in the north. If they wanted to have a plant to cheer them up during the winter, our desktop greenhouse would help them out.
This is Connect 4. The idea is to use Mechatronics to interface with a real-life board game so that people can interact with the computer. So what you'll do with this project is you drop a token into the Connect 4 game, and then the computer senses where you drop it and then calculates the best place to move and then moves itself. Yeah, it's a lot like chess, except a much simpler game.
I'm
sorry, I wasn't.
This is the Delta Droid. The idea behind it is that we wanted a machine that was capable in real time of reproducing human motion. It can move in all 3 degrees of motion and keep up with your hand as it's moving on a computer just as quickly and as agile as you want it. And from that, we decided, what can we do that's interesting? So we decided to add on an extruding stage with frosting, so then you can put a cookie in there and you can extrude frosting and draw it just as you would try to in your home with a normal frosting extruding.
So this is Fido. Fido is a spherical robot, and right now he rolls and is controlled based off of this controller. It's basically like a joystick. Any way that you turn the joystick is where Fido will go. The special thing about Fido is he's self-balancing, so that if you had a spherical robot that didn't have self-balancing, it wouldn't be able to roll because it would just always be falling over to one side. So what we've done here is we put in a weight carriage that it's on a closed loop basically, so that it itself knows how to balance itself, so that all you have to worry about is setting the robot where you want to go. Like, a lot of people think of like, oh, this has to be immensely useful and solve every single problem known to mankind. But honestly, it's just kind of a fun personal assistant. We were thinking it can carry things, it can be like a mobile hotspot, you can put your cell phone in it, it could go get your coffee for you, you could just put, a little cup holder in there and just, oh, don't talk to me, talk to Fido, my personal assistant.
So we built a camera gimbal that tracks a color in 3-dimensional space. So our subject, wearing a blue shirt, it's able to follow him up and down, left and right as he moves around in space. Basically, you tap the color on the screen of the camera phone, and then it finds the centroid of his shirt, sends the centroid to our Arduino. The Arduino talks to the motor control board, which then angles the GoPro as it needs to follow him. So if we detach it, it also stabilizes using accelerometers and gyroscopes, and can also track him while it's stabilizing. So an application would be to attach this to a quadcopter, and basically you could be skiing down the mountain wearing a bright colored shirt. It could track you, and it would keep you in the center of the frame of the GoPro camera. So then you'd have a great movie at the end of the day.
So this is my group's project. We call it Project Sidewinder because it's a mobile drive platform that's able to both translate and rotate. And we accomplish this by having 3 independently controlled modules. So each one of these modules can rotate and power the wheel separately from each other. And what this allows us to do is both translate and rotate at the same time. And this is different from traditional drive platforms like cars, because cars need to move forward and backwards in order to turn. And what this allows us to do is both turn or translate and move basically in any direction it wants, and it's able to do so.
So this is our project for 102B. We made a voice-activated safety helmet, so everything is hands-free. So let's give a demonstration. Open helmet. Turn on flashlight. Right flashlight up. Left flashlight down. Close helmet. And that's our project.
All right, so our project is doing a power-assisted wheelchair, and the idea is basically just to reduce the load on the average wheelchair user. So when I push forward, it'll push forward and give me a boost as well. So if I go slowly, it won't do much. Just the user function. If I give a bigger boost, it should turn on. So what makes it go? We have encoders behind it that are reading the position, and essentially we're translating that into the acceleration. And then from there, the motors are turning on, essentially, when we reach a certain velocity and acceleration.
All right, this is our ME102B project. It is a laser tracking system. It uses an image processing algorithm combined with a 2-axis gimbal that we designed to ideally keep a laser on top of a target while it moves, including through fast motion. An application that was brought up to us that we hadn't even thought of was particle flow velocimetry, which is where small particles in a fluid flow are measured to track streamlines.
So this is an automatic bicycle transmission that will shift the gears for you as you change your cadence. So as the RPMs on the pedals change, it changes the gears along with you. So the servo mechanisms right here, they pull on this wire, this gear cable, and that's what shifts the chain back here, and it changes gears. But if we slow down, it'll begin to downshift. And so right now we're going at about 20 RPMs, give or take. And so after a couple revolutions, it'll take the average of those RPMs, and then it'll calculate what gear to go to after that, and it'll downshift to that gear. There we go. So now, like, the cyclists can go around and they can just keep their hands on the handlebars without having to think about shifting gears or anything like that. They can keep their focus on just riding.
So we're using 3 motors here and a lot of programming to make pictures onto a cylindrical object, sort of dot by dot. And we can process any image that we put into our code on the laptop, and that sends a signal to the embed, which is a microprocessor that tells the motors what to do. And the pictures look like this. They come out like this bear. So, and we can do any picture or any text.
All right, this is the scripter, and what it does is it takes an image, any image you can upload into MATLAB, and it processes that image into a path. From that path, it's translated into Arduino, and our control algorithm has this vehicle follow it using some magnetic encoders on the bottom of the vehicle. The idea is just being able to take any image and blow it up as big as possible, and so you don't have to be confined by the limitations of having a physical printer, which can only print up to a certain size.
Hey, my name is Kyle, and I'd like to present to you the Princeria, the world's first 3D Theta food printer. So as you see, we use a very unique pneumatic system to drive the food through these tubes out to the nozzles. This is the one of the highest capacity food printers. We have a lot of foods around, a lot of sweet foods and a lot of savory foods are around, and we thought it'd be nice to have a stage that very accurately represented the round shapes that we wanted to make with the foods. So in a traditional Cartesian system, you have an X and Y stage, which would be like up, down, left, right. But instead of that, what we have is we have R, which is increasing radius of a circle, and theta, which is the number of degrees you go around the circle. And by using these two coordinates, we can still create a full coordinate system where we can print pretty much anything in the same amount of area, but in a smaller amount of space. And as far as we know, there's been no other food system that uses this printing method for making food.
Our big idea is to make these sorts of popular little sports cameras a bit easier to take nice video with. And this is our camera stabilization gimbal, and it lets you hold a camera steady without paying attention to the orientation of the base. This is just a fairly rough prototype here. So you've got a motion sensor, an inertial measurement unit, and 3 servos, and an Arduino to control it. It just and plus this hand controller, which lets us set an orientation. Once you set an orientation, it holds that orientation steady regardless of the position of the base.
But basically, if you're in a car and the sun's shining from the top, depending on the angle, these glides will come down. Our device is called Smart Shade. So if I shine this flashlight at the sunlight sensor at 4, it will go all the way down. And then up here, it's more of an intermediate stage. So it goes all the way back. And then there's also the side shade. Kind of went from the other side. Maybe depending on where you put the light, the shades adjust and move accordingly.
So this is our quadcopter here, and we have an Android phone attached to it. The quadcopter, as you can see, it's right here, and the Android phone has an Android app on it that essentially is able to track the X and Y coordinates and then feed that information to the quadcopter. And based on that, the quadcopter is able to turn left or right in order for the object to be centered back into the center of the phone. So applications involve general surveillance as well as security. Since it's able to track any type of object, it has a wide variety of applications, but security and general surveillance is one of the major applications for this type of project.
Okay, Scanier is a cost-effective solution for being a 3D scanner. So what it does is it uses infrared sensors to take a model of any solid object, and it generates a computer model that you can use to 3D print. It's really fast. An object like this mug would only take about 40 minutes to scan, and then once you have the model of it, you can immediately send it to a 3D printer and get that print right away.
Right now he's just trying to